Okay, in this video, I'm going to be covering what's called the integrated rate law, and eventually move on to calculations for half-lives of reactions. So, first of all, a little bit of background on what we're trying to talk about here. So, I'm going to start with this graph right here. All right, we're going to compare this graph to another graph that we're going to be deriving an equation for in just a second. But if you were to have a first order reaction, all right, and again, that's one where if you double the concentration, it would double the initial rate. Here's what the concentration of that reactant would look like over time. All right, so as time goes on, this is your reactant, and so the concentration of your reactant left is going to be going down over time. All right, but notice it doesn't happen in a straight line. It happens in kind of a curved type of a graph where you get this eventually get this asymptote that never actually reaches zero. I mean, it gets really, really close to zero, but not quite. All right. So if I were to say what is the exact concentration at any given point in time, all right. Well, if the concentration happens to be at an exact point in time that I've got a data point for, I could give that concentration. But what if I were to say, what would the exact concentration be at this exact point in time? All right. Well, if we're looking at it graphically, we could go up and find that point and kind of try to estimate what that concentration would be. But one thing that you might know if you've taken calculus is that there's a way that we can determine what these exact concentrations would be at different points in time by using a little math. All right. So I'm just going to, before I do this, I want to point out that even though there is calculus involved in the deriving of these equations, first of all, I'm not an expert in calculus. I know just enough to hopefully describe this and relate it to your class. But I do want to point out that as far as I know, for IB, you are not responsible for knowing how to derive this equation. You're just responsible for knowing how to apply the equation. All right. So like if I do think though that since most of you guys are taking calculus, it would be interesting to see the connection between the chemistry and the calculus. All right. So let's go and start off with what we know. All right, so first of all, let's start with just focusing on the left side right here. All right, this is an expression for rate. All right, remember when we're talking about measuring the actual rate of an equation, we can only measure what we can see. All right, so we can either see the disappearance of a reactant or the appearance of a product. All right, and so this is focused on the disappearance of a reactant. So we're talking about the change in the concentration of a reactant divided per how much time that change occurs over. All right, and remember we put a negative here because we always want the rates of our reaction to be a positive. All right, remember the disappearance of a reactant is an indication that the reaction is proceeding forward. All right, so that's why you need the negative there to compensate. All right, and we're just going to go ahead and assume that this is a reaction where you have a 1 coefficient in front of the A, and so therefore we don't have to worry about dividing it by half. All right, so that is the literal definition of the rate of a reaction. All right, but we also learned that when we were deriving our rate laws, that the rate of the reaction generally is a function of the concentration. It can be either first order, second order. All right, but this is the part where we say that the rate is equal to some constant times whatever that initial concentration is. All right, so that's the KT. And since these rates are going to be the same, we can relate them to each other. All right, so remember what this part right here says. This is not an instantaneous rate. This is an average rate. If I had something in the beginning and then something a minute later, I could say, well, what is the overall change in the in the concentration, and this would be the overall change in time. All right, but what we're interested in is instantaneous rates of reaction. All right, so if we turn this into an instantaneous rate, we express it like we would in calculus. We say dA, the infinitesimal change in the concentration divided by the infinitesimal change in time, all right, equals Ka. All right, so what can we do with that? We're going to essentially, first of all, we're going to take this negative and we're going to put it on this side right here. And we're going to rearrange this a little bit like we would in calculus, where we're going to move the A to this side and we're going to move the dt to the other side. Oops, sorry, let me... All right, and you end up getting this expression right here. All right, and so hopefully this is starting to look like something that you would see in calculus, where, all right, looks like something that we're going to be able to integrate on this side and something that we're going to be able to integrate on this side. Notice that K is a constant, all right, and I think you guys know that when you have a constant, you don't have to, you can put the integral, you don't have to put that as part of the integral, right? So what we're going to do is we're going to integrate the left side from, so we're going to integrate from time 0 to time equals t. All right, so what is the concentration at time 0? We represent that as the concentration of A at time 0. What is the concentration at time equals t? That would be represented by A with a little t down here. And again, we can integrate here, pulling the K out. And if you just pretend that these are x's instead of molarities, hopefully you might know the integration rules, and that's going to develop. You're going to be able to say it's going to be the natural log of x minus the natural log of x, and you evaluate it from the upper limit to the lower limit. We're going to do the same thing. If you integrate just plain old dt, it's just going to be time minus time of 0, and since the time at 0 is 0, anything minus 0 is itself, and so you just get minus kt. All right, so I want to point out that this expression right here, because of the rules of natural log, would be the exact same thing as this expression right here. All right, so depending on what you're asked to do, we could use either of these. But this one right here is the one that we're going to focus on, because we can take this right here and rearrange it. All right, so what I'm going to do here is I'm going to move this ln of at over to the other side. And why would I be, oh sorry, what I'm going to do is move the ln of a0 over to the other side. So that gives me this expression right here. The natural log of the concentration of A at some time is equal to negative Kt plus ln of the, and again, this is the original concentration. All right, so why is this useful? Notice that this follows the general line format. All right, y equals mx plus b. All right, so we could take this and this, we could put this as our y coordinate. All right, so notice what I'm doing here is I'm graphing this is my y coordinate. Mx, all right, so the x axis would be this, t. All right, the natural log would be the natural log of the original concentration would therefore be our y-intercept. All right, so if we were to take this, and let's say that we measure this at a range of different, we do this over time, what you're going to see is that, okay, so again, what's going to happen here is that for a given starting concentration, all right, if you measured the overall concentration versus time, what you would find is that the natural log of that concentration versus time would make a straight line. All right. Notice that if we were to take the exact same data and we measure the exact concentration at some unit in time versus time, we don't get a straight line. All right. So one of the hallmarks, one of the things that you're going to be expected to know is how to spot whether something is first order given a data set. And one of the easiest ways to spot that something is first order is if you plot the natural logs of the concentrations versus time, it's going to give a straight line. Whereas if you and that's going to be the hallmark. All right. So one thing I wanted to point out, there's a name for this equation right here. It's what's called the integrated rate law, and the name comes from the fact that it comes from integrating the reactions, or sorry, the rate laws that went into it. And but I also want to point out that this right here is the integrated rate law for a first order reaction. All right, so this would not work if the reaction was determined to be second order. Okay, can we do the same type of thing for a second order reaction? And we can do that right here. So again, remember, this is again, the overall rate part is the same. We're measuring the disappearance of a reactant over time, but the rate law, since it's second order, would look something like this. All right, and we're doing this for a case where it's second order only with respect to one of the reactants. All right, so again, we can rearrange this, moving our A's over here, move actually that should be dt over there. All right, and again, that should be dt right there. So that when we integrate this, we end up getting this expression. All right, when you integrate this function right here, you're going to get -1 over AT. All right, so when you evaluate it from these limits, the first one you're going to get is when your concentration is this. All right, you're going to subtract that from your what you get when you use this for your concentration, which gives you this expression right here, and that expression can be rearranged to give you this right here. And this is generally what we use as the integrated rate law for a second order reaction. All right, and again, the reason that they choose this particular way to do it, where they put AT on this side and they put A0 on this side, is that it follows the line format. This is something that we could put on a y-axis. Time is something that we could put on an x-axis, and this right here is going to be a constant that that would correspond to the y-intercept. All right. So comparing graphs here. All right. This part right here is kind of important. All right. We can take the data and we can do different types of graphs with it. Okay, so this part right here is kind of important. You can take your original data and you can graph it several different ways. Okay, and so let's say that we took our concentration. Actually, this should be ln of AT right here. Let's say that we tried doing with this data what we did when it was the first order equation. Remember, when it was first order, if we plotted the ln of the concentration at some time versus the time, we ended up getting a straight line. Well, in this reaction, if you try doing the same thing, you don't get a straight line. So what that tells us is that this reaction would not be first order, because if it was a first order, when we did this plot, we would end up getting a straight line. All right. Instead, what we find is that if we plot 1 over AT versus time, we end up getting a straight line here. Remember, for a second order reaction, you should get a straight line because this right here follows a straight line format. All right. So when you do this, that's a hallmark of saying this is second order. All right. So I just want to point out, notice that this is the graph that you use for first order. And since we're putting second order data into a